In the previous video, we saw heap data structure. In this video, we are going to extend it and learn heap sort. Just for the sake of revision, let's look at what is heap. Well, heap is a data structure that follows below two properties. It should be a complete binary tree and the value of root must be largest among all its descendant nodes. The value of any node must be largest among all its descendant nodes. We store this particular tree in dynamic array. In C++, that is a vector. We saw four different operations on the heap. First one was insert. So we used to add new element at the end of the array. Now that newly added element might end up breaking our heap properties, right? So we used to check that element with its parent. If the value of parent is smaller than the newly added element, then we used to swap. And we used to continue this until we place the new element at its correct position and all the heap properties are satisfied. It has log n time complexity. After that, we learn about a delete operation where we used to swap the node which we want to delete with the very last node. Then we used to remove the last node. After that, remember, our swap might have ended up breaking our heap properties. That's why we need to heapify the newly placed element or the newly placed node. It used to take log n time complexity as well. Now heapify is a recursive operation that is used to place any node at its correct position. Even though we mentioned that it is a recursive operation, this operation can be easily coded in an iterative way. So this is the logic. We find the largest node, the current, left and right child. We check all the values of these three elements and find the largest. If largest is the current node, then we break it. If largest is left child or right child, we swap the current node with left or right based on the largest value, and then again we heapify. If largest value is left child, then we heapify left child. If largest value is right child, then we heapify right child. So why do we swap? Well, we are talking about max heap, right? And the property is it should be a complete binary tree. And second property is for all the nodes, value of current node should be largest compared to all its descendant. But if the largest is not equal to the current node, then we are going to swap it. This heapify operation also takes log n time for a single node. Imagine they provide us a random input array. We heapify all the nodes, then we will ultimately have a heap. That should take n into log n time. But we saw the proof that it will only take O of n time. Now let's try to build the logic for heap sort algorithm. We are going to use the second property of heap. What was the second property of heap? For all the nodes in the tree, the value of current node should be largest among all its descendants, correct? So we know for the fact that the value of root node is going to be the largest, right? Because this should be larger compared to all its descendant node. Imagine they provide us an input array with random numbers. We perform build heap operation on it and we get a heap. Now we know that the root value is going to be the largest. So we are going to place this root value at its correct position. What is the correct position for the largest value? Where is the last position, correct? So we are going to place this 15 at n-1 position. So how are we going to exactly place it? We are going to swap the last element with the first element. Now we have 4, 5, 7, 2, 3. Now this swap has ended up breaking our heap property, correct? Similar to the delete operation. If you look at my implementation of delete operation from the previous video, you can clearly see that we are not actually swapping it there. We are assigning this 4 to the very first position and we are removing the 4 itself. So 4 will go to here and we remove 4 itself. But I pointed out then and there itself that we can also use a swap operation. I purposefully did that so that I can highlight the same thing here and it will be much more easier for you to understand. Now once swap operation is performed, you have 4 here and 15 here. This swap might end up breaking the second property of heap. We are not sure. But if you look at our current example, this 4 is not at its correct position. So this swap operation has ended up breaking our heap properties. So what we need to do? We need to heapify our node 4. But if we heapify, this 15 will go to the root again. So there is no point in swapping, right? That's why we are not going to heapify the entire tree. we are selectively going to heapify this tree only. We are going to remove this 15 from our consideration. All the further operations are not going to affect the position of 15 because we found the correct position for 15, right? 15 is marked as green because it is placed on its correct position. Now we are going to perform heapify operation on our root element, that is 4. So it will check for the largest value among the 3. 7 is the largest, so we are going to swap 7 with 4. And now we have the proper heap. If you look at my heapify code from the previous video, a video on heap data structure, you can clearly see in heapify operation that we have this check. Left should be less than n and r should be less than n. By controlling the value of n, we can control which portion of the tree we are going to heapify. So when we are heapifying this entire tree, what we can do, we can pass n-2 to our heapify operation rather than passing n-1. If we pass n-1 to our heapify operation, this entire array will be heapify. But if we pass n-2 to our heapify operation, it will heapify only the first n-2 elements, because we know that 15 is placed on its correct position. So now I hope that you understand that check as well. Usually we don't discuss that check, we only say if largest element is equal to the left child, then we are going to swap and heapify. But this is the half truth. We also need that check where we are controlling the portion of the tree that we are going to heapify. So now we have this particular tree, correct? Now 7 is the second largest element. How do I know that? Well, we have removed 15 and whatever we have now is a heap. So that means the root node must be largest compared to all its descendant. So 7 will be largest compared to all its descendant. So 7 will be the second largest element and we place it to n-2 position. So once we do that, we will have a tree something like this. Again, we need to heapify, but if we heapify, this 7 will reach to the root. That's not what we want. So we are going to heapify only this tree, correct? So to heapify operation, we will now pass n-3 because the last two elements are placed at its correct position and we know that. Okay, those 7 and 15 marked as green because they are in their correct position, and we are going to heapify our first 4 elements. We have 3, 5, 2 and 4. So we are going to heapify the root. Why are we always heapifying the root? Remember, we are swapping the last element with the first element. So every single time we do a swap, the root element itself is going to break the second property of heap. That's why we always need to heapify our root element only. In this case also, we are going to heapify our root element. 3 is the root element. It will check for the largest value to the left, right and current. So the left value is the largest value and it will swap 3 with 5. Now we have this heap, right? Now we know that 5 is going to be largest element because 7 and 15 are fixed. Now we are going to swap 5 with the last element, which is 2. So it will be something like this. Now this swap has broken our second property of heap. We are going to again heapify our node 2. But we cannot heapify directly because this 5 will climb up again. So we need to heapify only the first 3 elements, that means n-4. 5, 7 and 15 marked as green because they are placed in their correct position. 2 will check who is the largest among 3, 4 and 2. 4 is the largest, so it will swap 2 and 4. So we will have a heap something like this. Again we know that 4 is the largest element. We will swap 4 with the last element, which was 2. After the swap, we have a heap something like this. We are going to heapify only the first 2 nodes because the 4, 5, 7 and 15 are placed on their correct positions. So once we heapify 2 and 3, we have a heap of 2 elements, 3 and 2. Now we know that 3 is the next element which is the largest and it has not been placed on its correct position. So we take the 3, we swap with the last element and we will have something like this. Again, we are now only going to heapify our node 2 because 3, 4, 5, 7 and 15 are now placed on their correct position. So heapifying a single node is nothing, and ultimately we will have a sorted array. So by using the second property of heap, we managed to build a heap sort algorithm. Here we use heapify operation heavily. So here we will have total n elements and we are performing heapify operation n times, right, for all the elements. So the total time complexity is going to be n log n. Let's try to convert our logic into the code. So given an input array where elements are arranged in random order, we are first going to build the heap. Once the building of the heap is done, we take the largest element, that is the 0th element, and we swap that element with the last element, that is n-1 element. After that we heapify first n-2 elements. In the next step, we take the largest element, we swap with the n-2 element and we heapify first n-3 elements. And we do this until we reach node 1. That's why we have a for loop here. Look at this, I starts from n-1 till it reaches 1. We are going to swap the first element with the last element. See, this is the swap operation that we have. We are swapping first element with the last element. I is iterating from right to left. So here we are swapping the very first element with the very last element. Then we are going to heapify the remaining elements after the swap. So array is the input, I is the limit, total number of elements that we are going to consider for heapify operation, and this is the index of a node that we are going to heapify. Remember, we are always swapping the last element with the very first element. So the element that is going to break the heap property is going to be the root element, that is the 0th index. That's why we always heapify the 0th index. So we managed to convert our logic into the code. First we will build the heap from the input array. Then we iterate on the given array from right to left using this I iterator. We swap the very first element with the last element because we know that first element is going to be the largest one. Once the swapping is done, now our root element might end up breaking the second property of heap. So we need to heapify our 0th index, but we are not going to perform heapify on all the elements. We are going to perform heapify on selected few elements from the start, and that we consider by using an iterator I. Let's look at the code. This is the heap sort and they are providing us the input array. First we build the heap by doing heapify on all the non-leaf elements. After that we start our loop. First we take the largest number and place it to the last position. After that we heapify our 0th index and only n-2 elements. From 0 to n-2 elements inclusive. That means from 0 to n-1. And after this loop we will have a sorted array. As we have already mentioned, the time complexity is going to be n log n. This build heap is going to take O of n. This heapify operation takes log n, and we are performing this heapify operation n-1 times. That means n log n will be the time complexity of this heap sort. Let's look at the heapify operation. This is the index on which we need to perform the heapify. This is the limit for us, and this is the input array that we have. So we assume that our current node is going to be the largest one. We compute the value of left child and we compute the value of right child. We check whether our left child is within the boundaries and the value of left child is greater than the value of the current child. If that's the case, then we will update the largest index. Same thing we do for the right child as well. If largest element is not equal to the current element, we are going to swap and heapify. If you don't understand this heapify operation, please do comment. I can make even more detailed video on this. So till now we have seen bubble sort, insertion sort, selection sort, merge sort, quick sort, and this is the heap sort. We have seen multiple sorting algorithms. Please go through them all. This is the last sorting algorithm we are going to see in this series.